Hello and welcome to this clip on spotting procedural errors in chemistry. I've put it together at the request of students who want to have some reaffirmation of what you need to do when you're spotting errors, what constitutes an error, and how it might affect your final result. So the four main practical techniques that we use in chemistry where errors can pop up are titrations, gas collection and measurement, heating to constant mass, commonly to determine the number of moles of water crystallization in a hydrated salt, and measuring an enthalpy change using calorimetry, in other words, Q equals mc delta T. So in each case, what we'll be looking at is during the various stages of a procedure, if you do a certain thing at some point in that procedure, why it constitutes an error, the knock-on effects that will have on your final measurement, and how you can actually prevent that mistake being made, where applicable, of course. So in order to do this, you need to get comfortable with a couple of ideas. This doesn't automatically come to everybody, so it will take some practice and some thinking and a willingness on your part to actually sit and think your way through the actual mathematical consequences of a change in a measurement. So to do that, you need to keep focused on what's happening to the moles of the reactant. Are you losing moles at any stage? For example, transferring a liquid. Have you spilt anything? Will that affect the number of moles that are reacting? And therefore being able to predict in your head what will happen at the end of the calculation. So think about the calculation that you're doing. Is it a division? Is it a multiplication? And if a measurement is lower, for example, midway through a stage of a calculation or a stage of a practical, will the answer to the calculation at the end actually end up getting bigger? So you have to think in terms of ratios. So being able to do that and do it effectively is key to being able to think your way through these types of problems. So let's start off with the calculations and titrations. So let's look at what a titration actually is. So this isn't a definition of it, but it's more of an explanation of what it's for. So we use a titration to work out the unknown concentration of a sample of known volume. The sample, it doesn't matter what it is, we might know what particular substance it is, such as hydrochloric acid or sodium carbonate, for example. So what we do is we make up a standard solution of something that reacts with that unknown compound, or the compound that has an unknown concentration. If you know what the mole ratio is between your compound of unknown concentration and your standard solution, then you can work out the moles that are needed for a complete reaction. So you take a titer using a burette, and that titer will tell you, or if you do 2 or 3, and you make sure you get an average, you use your average titer to work out the amount of moles needed for a complete reaction. So the first thing you do is you put your unknown concentration, your solution of unknown concentration, into your conical flask. So you put your standard solution into a burette, making sure of course the tap is closed so none of it accidentally falls into your solution being titrated. And what you do then is add a few drops of indicator to your solution being titrated, the unknown concentration. And then you add a few drops of indicator to your unknown in your conical flask, and you're ready to start. So what we'll do now is look at the titration in several stages, and we've got video clips built into this particular clip, so little short clips of the different stages, so we can discuss at each stage what needs to happen to ensure accuracy. So the first stage in your titration, if you're doing it from scratch, is to prepare your standard solution. So to prepare any solution of a known concentration, you have to weigh out an exact amount of solid. What we do is we use a weighing bottle of some kind, like you can see in the picture, and we pour a set amount of solid into there, and we need to make sure that the amount that we put in there is as accurate as possible. So the reason for that accuracy is because an exact amount of moles of solid is needed if we want to know what the exact concentration is. So if we look at 2 common procedural mistakes that will affect the amount of moles that's actually reacting, the first one is spilling some solid onto the balance itself. So the balance will pick up the mass of that solid, but because that solid isn't in the bottle, it won't go on to react, because you're only going to transfer what's in the bottle into a beaker to dissolve it. So this will be the moles that are actually reacting will now go down, but you won't realise that, because you'll be taking the moles calculated from the mass that was measured on the balance. The balance can't tell between solid that's in the bottle and solid that's sitting on the metal tray. If you use the zero function on the balance, when you transfer your solid into a beaker to dissolve it, a small amount will be left behind in the bottle. No matter how hard you try, there'll be a few crystals left in there. That will lower the amount of moles reacting even further. So what do you do? So to avoid spillages, you might want to put the solid onto a piece of paper, and then from the piece of paper you have the piece of paper folded, and unlike the picture, instead of emptying it directly from another bottle, you could empty it from a folded piece of paper, so it just slips down the folded edge nicely like a funnel into the bottle. Instead of using the zero function on the balance, measure the mass of the emptied bottle afterwards, because that will have the left behind few crystals in it. The difference between that and what you managed to measure in the first place will be the exact amount that's ended up in the beaker. So you're not actually losing any moles as such in your calculation. You may end up with a little bit less of the solid that you started off with or that you intended to measure out, but at least everything that's going to be transferred into your beaker will actually end up reacting. So you will not be thinking that there's more moles of reacting solid than there actually is. So the main problem in the dissolving your solid stage is if when you've dissolved your solid in a beaker, usually make it up to about 100 centimeters cubed, then you transfer that into a volumetric flask. If you don't rinse the beaker afterwards and then pour your rinsings into the volumetric flask as well, then you'll risk leaving some moles behind yet again. So the key thing to think about here is when you transfer solids or transfer liquids, moles might get left behind. So one way of spotting a procedural error is if there's a stage where you transfer something from one container to another, make sure you don't leave some of it behind. You transfer as much of it as you possibly can. So good practice is always to try and rinse to do that, particularly when dealing with solutions. So the next stage in your preparation of your standard solution will be to make it up to the mark, as we say, in a volumetric flask. So the volumetric flask in the picture is in steps C, G and E. It's the sort of round shaped vessel with a long neck. So basically you pour your prepared solution, your 100 centimeters cubed in the previous stage, in step C into your volumetric flask. And obviously the 100 centimeters cubed is going to be less than the size of the volumetric flask. So generally we use volumetric flasks of about 250 centimeters cubed, but you can get them in lots of different sizes obviously. So in step D what's happening is you're topping up the final part of that with water. So you make up to 250 centimeters cubed by adding deionized water to the solution you've poured into it in step C. So there's a possible source of two mistakes here. If you put too much in, your solution is going to be too dilute and there's not enough moles per given volume. And if you don't add enough, there'll be too many moles per given volume. So what's going to happen is the only mark is going to be at 250 centimeters cubed. So if I, for example, put a line there and a line there, that will be where the mark is etched into the glass. So you have to make it up to that particular mark. So to do that accurately, you use a pipette to add the last few bits of water. So let's say that we assume that in E it's been done accurately. That means that my line needs to correspond with the top of the liquid there. So that means that what I'm doing in step D is adding my last few drops of water bit by bit. Because if I get too much, then it's going to affect the dilution. If I get too little, it's going to affect the dilution. So if you have a concentration in your volumetric flask that is actually inaccurate, what's going to happen is that's going to affect the size of the titer The titer will either be too small if there's too many moles, or too big if there's too few. So now let's have a look at the stages of the actual titration part itself. We've now made up our standard solution. This will be the solution that goes into the burette. So we've made up 250 centimetres cubed. We're going to use 25 centimetres cubed portions of this to carry out each individual titration. So we may not use all of it up, but the important thing is that the concentration of it is correct and accurate. So I'm going to play these clips I made a couple of years ago. I've embedded them into this YouTube clip. So I'm going to play them one at a time, and what I'd like you to do is to grab a piece of paper and see if you can come up with a possible answer to the questions in pink. So the clips are about a minute long, so I'll play them in quick succession, and then when I've played all three, I'll come back and put the answers in. But I want you to have a think about it and pause the video to let you have a think first, instead of just waiting to be given the answer. Okay, you can clearly see that the bottom of the meniscus, I've added some of the sodium carbonate solution, and it's slightly above the 0 mark. So what I'm going to need to do is to turn the valve and slowly let a little bit out so it can creep down towards that 0 mark, like that. Okay, now even then I've gone slightly over, so you can actually see I've gone down to 0.1. So ideally when you start, you need to have the bottom of that meniscus directly on the 0 line. So in this particular titration, my standard solution was sodium carbonate, a weak base. That's why I referred to it in the clip. So now let's play the second clip. Okay, so I've set up a brand new titer with 4 drops of methyl orange added. So now I know I'm aiming to get it fairly close to around 21. But this time I've got to try and get it exact, because last time it was a bit of a rough titer. So I know the ballpark figure to aim for. So I've topped up my burette again. Okay, so if I start adding this, I swirl as I'm adding it, and I keep an eye not only on the colour, but also how much I'm actually adding. Okay. The colour's not changing yet, but you'll notice as it touches, So I'd already done a rough titration. I knew to expect it to start changing to around 21-ish. So you can start to see about here the colour is starting to change already. So I just want to make it clear that in this clip it's approaching the end point. So we're not actually reaching the end point, it's approaching the end point, so just so we're clear on that. Now the next clip is actually judging the end point, so trying to get the colour just right, so it's not too much and not too little. So picking up where we left off a couple of seconds ago, you can clearly see that we're now approaching the 21 mark. So I've stopped the flow of liquid, and now what I'm going to do is I'm going to change it to dropwise while still shaking. So you have to carefully turn the valve, slowly, ever so slowly, so it's now a much more controlled addition of liquid. And looking closely at the liquid, holding it over, you can start to judge that it's quite close now to a colour change. So give that a shake. I've stopped the flow of liquid, and now that colour change is maintained, so you can call that a more accurate endpoint. So now let's have a look at the answers to those questions. So in the first answer, the titer would be too small because you'd reach the end point using a volume of partially unmeasured standard solution from above 0 centimetres cubed. So in other words, if you were to have the liquid starting here somewhere,
then that would mean, actually what I'll do is I'll make that in pink against the blue background. So if let's say you were up there somewhere, that section of liquid wouldn't be being measured, but it would be contributing to the neutralisation. So the remaining measured amount would be smaller. So what would happen is you'd have a smaller volume, smaller titer, being used for neutralisation. In the second question, the measured volume is going to be V. So if you divide the number of moles by a bigger volume, let's say you add too much and you overshoot, the bigger number on the bottom of that expression is going to make the value for C smaller. So the value will be too small because the measured volume needed for neutralisation would have been too big. In the third one, the burette's measured from the top because it's a piece of glassware that measures the amount you've emptied out of it, not like other pieces of glassware which measure the amount you add to them. So because you're measuring the emptying of the glassware, you start from the top where you fill it up to, instead of starting from the bottom where you fill it up from, as in other pieces of glassware.
So here's another one to think about. I'm going to demonstrate adding some of the solution of unknown concentration, which in this case happens to be hydrochloric acid. So I'm going to add it to the conical flask, ready to titrate it with the sodium carbonate. If I used a pipette where the inside surface of it was wet, what might happen to the value of the titer? Okay, now we're going to set up the titrant. The titrant is the solution for which you're trying to find the concentration, in this case hydrochloric acid. So using a pipette, a glass pipette and a pipette filler, we draw up 25 centimetres cubed of the acid, using nice slow movements of the thumb at the top. And when it gets to the etching of the glass that shows that you've reached 25 centimetres cubed, you simply transfer it into the conical flask, like so. When it reaches the bottom, you touch the end of the teat on the pipette, just on the glass, surface tension to draw the liquid out, and push the last few drops out with the plunger at the top, put it down. So now pause the clip and have a think about what the effect might be, and resume playing when you're ready. So it would lead to a lower titer, or lower value for the titer, because if you had water on the inside of the pipette, it would have the effect of diluting the concentration of the solution that we don't know the concentration of, so it would make it seem artificially low. So there'd be less moles of the solution inside that 25 centimetres cubed that you're transferring using the pipette. So to get around that problem, what we do is we rinse the pipette with the solution you're transferring. So we take some solution from the volumetric flask and rinse it through into the sink, and then the inside of the pipette is actually coated in the solution it's trying to transfer, so that won't affect the number of moles. So now we're going to shift on to measuring gas volumes. They sometimes ask questions on this too. I'm also going to increase the pace a little bit because it's time to start seeing if you can run with some of the ideas that we talked about before, but this time apply the basic principle to a new technique, not a titration this time. So this is one of the things we talked about right at the beginning, wasn't it? Getting comfortable with looking for areas where the correct number of moles is being disrupted somehow, and how will that affect your calculation. So imagine you've got this set up. It's a reaction mixture, and maybe it had to be heated slightly, so we can assume maybe that it was on a tripod with some gauze, and we can add some gentle heat. Just to get it moving. So you get some gas coming off, it starts to fill the conical flask, and eventually the syringe, the plunger, starts to move, showing that there's some gas being made. Have a look at the 4 questions and pause the video, see if you can think about what the effect of each of those things might be on the value of n. So N will be the moles of gas that are made when the plunger stops moving, so when the reaction is completed. And then resume the video when you think you might have some answers, and we'll see if we agree. So hopefully we're generally in agreement. What I'm trying to do all the time is think about what is the effect of this change going to be, if any, on the number of moles. So if you stick to thinking about the number of moles when you're doing these kind of decisions and questions, you can't go far wrong. So let's now move on to another technique that commonly comes up in questions about practical skills. So here's one for you to take a few minutes to try. Do a rough sketch of each of these in your notes and see if you can explain why the gas syringe setup on the left is more accurate than the test tube and inverted graduated measuring cylinder setup on the right. Pause the video now and we'll come up with some ideas after that. So hopefully you were able to spot two things. First of all, the gas is dry, so if it happens to be slightly soluble in water, none will be lost during the measurement process. If you were to pass it through water, collect it over water, in the other diagram at the bottom right, you can see the bubbles have to travel through some water and therefore some of the gas might dissolve. That will affect the actual amount that you're measuring. The second thing is the gas syringe is more sophisticated anyway. It's a much higher precision, higher quality piece of equipment compared to a measuring cylinder, so therefore it's more accurate in its use. So don't forget that pieces of glassware for measuring come in different sizes, and smaller measurements tend to have a larger range of uncertainty because the effect of any mistake is going to be bigger on a smaller volume that's being measured. So here's another one to try. Do a rough sketch of this in your same notes where you've done the other sketches just now, and see if you can work out why this is a better setup than the previous one that we looked at in the previous slide, where we decided that this was the better of the two. So this is an improvement further, but I'd like you to think about why. So this piece of equipment was designed to get around the problem of losing gas when you take the bung off to add the second reactant. So you add the liquid reagent through the dropping funnel, and it makes sure that the whole system is sealed. So the only place that any gas that's produced can go is into the gas syringe. So we'll now move on to have another look at water of crystallisation from a practical skills viewpoint. So I won't be going through how to calculate it, I'll be going through how different mistakes during the measurement process could affect the number of moles of water of crystallisation that you're trying to work out. So a quick recap. Basically what we do with measuring the moles of water of crystallisation is to take a set amount, a measured amount of hydrated salt, so you know the mass of the hydrated salt. You heat it to constant mass, so you're driving off the moles of water of crystallisation, and the difference, once you've done that, between the anhydrous version, which is the version with no water of crystallisation, and the hydrated salt that you started with, that mass difference is the mass of water that it contained. So obviously, knowing that the MR of water is 18, you can work out how many moles, in other words, the value of X, of water that the hydrated salt contained in the first place. So you've got three scenarios. What I'd like you to do is pause the video and see if you can work out what the effect on the value of X might be in each of these cases. And if you can, try and explain why. So, having a look at these three examples, in the example where some of the hydrated salt was spilt while its mass was being measured on the top pan balance, the top pan balance will pick up not only the hydrated salt that's being measured in the bottle, the weighing bottle, but also what's been spilt onto the actual pan of the top pan balance itself. So the result of this would be a smaller mass ends up in the crucible, so less mass of water is being measured by difference, but because the mass that you originally measured would be the total mass including the spilt salt left behind, that difference in mass would be assumed to be X. so this would make x bigger. If you hadn't heated to constant mass, then x would be smaller, as not all of the water would have been driven off, and some of the mass that you'd be assuming would be anhydrous salt would still actually be some water crystallization remaining. Let's say the crucible broke whilst heating. Nobody's fault, it just did. They do sometimes. But you checked with your friends and they said it was alright, just let it cool, and then scrape the mixture into a container and weigh it again. During that recovery process, you're bound to lose some material, so the mass of the anhydrous salt you actually end up weighing will be smaller, and therefore by difference to the original measured mass of hydrated salt, you're going to think that the bigger mass that you're measuring is due to more x, so it would make x bigger. So for our final technique, it's going to be Q equals mc delta T. By this stage you'll have done this quite a few times. So I've annotated each of the equations that you use. You start off by measuring Q, or calculating it at least, by heating a set mass of water and then measuring the temperature change. Then what you do is you get the moles of fuel burnt by working out moles equals mass over mR, and the mass being the amount of fuel that's actually burnt. So I'm going to set you a couple of questions to have a think about here, because this does turn up quite a lot in exams. So pause the video again and see if you can scribble down something that might address these two questions. So in the first instance, what would happen is that the value of n would increase because there's a larger difference in mass of fuel measured. More fuel would be being burnt, but some of the fuel being burnt wouldn't be heating the water because you removed the water earlier. So delta H will be smaller because Q will be bigger. In the second one, if you keep touching the side of the inside surface of the calorimeter, the thermometer will pick up the temperature of the calorimeter, not the temperature of the water. The calorimeter is usually made of metal, so it's likely to be able to heat up a lot more than water, so therefore Q is likely to be bigger, making the enthalpy change too big this time. So hopefully this has been fairly useful. It gives you the context in which all of these different practical skills are assessed, and maybe it will help you try some examples on some of the practice questions that you've done before, but see them in a different light. In the meantime, thanks for listening, and see you soon.